Hello everyone, welcome back to our session today. Our next speaker is Dr. Amir Abboud. Amir graduated from Stanford University, after which he worked as a research staff member at IBM Almaden Research Center, and then moved to the Weizmann Institute of Science, where he's currently a senior scientist in the Department of Computer Science and Applied Mathematics. His research focuses on understanding the exact time complexity of fundamental problems, and some of his other interests include graph theory and algorithms, dynamic data structures, pattern matching and sequence alignment, exact algorithms and parameterized complexity, distributed computing, and circuit complexity. Amir, thanks for accepting our invitation, and the stage is yours.
Thank you so much. Hi, can you hear me? Okay, hi everyone. I'm very happy to be here. So the plan for today is going to be two parts of the talk. The first part is just going to introduce this kind of body of works that we're calling fine-grained complexity. I'll, get us on the same page, like tell you the basics of this topic. And then I'll tell you some topics, some discussions of certain kind of newer directions that people have been taking this whole topic. So let's start. So this is like about complexity theory. And traditionally, the classical complexity theory, which you've heard of as the P versus NP and NP hardness theories, there the thinking was, we want to classify problems into those that we can solve efficiently and those that we cannot solve efficiently. And the thinking there was that what it means to be efficient is that you can find a polynomial time algorithm. And then this NP hardness theory lets us classify which ones we can and which ones we probably cannot. And fine-grained complexity is a more modern theory. We want to know, having a polynomial time algorithm is not enough. We want to know exactly what is the polynomial in the running time. So is it n, like linear, or is it n squared, quadratic, or what is it more precisely? And the thinking now is that what it really means to be efficient for us is near linear running time. So you really want to have near linear running times, and this is kind of partly motivated by the big data. Data is growing. Maybe in the past, n to the n squared or n cubed was fine, but now it could be inefficient. It's like a more modern complexity theory. And so, so why should you care about what is the polynomial? And of course, we care as theoreticians because a lot of the problems that you will see today, these are very basic fundamental problems. This polynomial time algorithm is very simple, like some dynamic programming or some brute force or something, and it's really fascinating to know if it can be improved or not. And so, of course, it's well motivated. But for those who want to tell their friends who don't do theory, why should you care? Here's just one example that I typically use to motivate this. So it's a problem from bioinformatics, local alignment problem. The definition will not really matter. So just the point is you get the two DNA sequences, they're very long, and you want to find the two pieces that are most similar. And similarity is defined with some scoring matrix, tells you, how much two letters match, and so on. And so your goal is to find these two substrings. And the point about it is you can solve this with dynamic programming, some simple dynamic programming in n squared time, so quadratic time in the input thing. And typically you want to solve it on huge data, so this n squared is really impractical. And so if you Google the name of this problem, Google Scholar, you get this other paper solving this problem. So it's one paper solving one problem with one algorithm called BLAST. It's heuristic, so it's not guaranteed to find the optimal answer according to the way the problem was defined, but it's linear time as opposed to quadratic. And this is like the largest number of citations I've ever seen. So this is one example where quadratic versus linear really makes a difference. And then so we want a complexity theory that can tell us, okay, so this is a problem we want to solve. We would like to solve it optimally, to find the correct answer. We would like to do it fast. Can we do it? Can we do it in subquadratic time, in linear time? And fine-grained complexity is trying to kind of answer these kinds of questions. And of course, that was just one problem. The class P has lots of fundamental, important problems. And for each one of them, we have some nice, simple, sometimes not, but some polynomial. We stop this. So there's this recent kind of empirical study of by some people from MIT about how important are algorithms for progress in technology and things like that. It's kind of like a strange paper, and this is what the MIT News says about it. That these scientists show that that algorithms, like faster algorithms, are critically important for advancements in computing. So like here's kind of a quote from the paper. So they basically looked at families of problems, like a lot of problems, and they said they look at over the years. Some of these problems were exponential, then polynomial, then maybe n cubed, then n squared, and so on. So they look at how much these things have been improving, and they put some reasonable constants and so on. And they show that for many problems, the improvements that you got from better algorithms are more dramatic or comparable to those you get from Moore's law, which is like about the hardware improving over time. And this is even when the data is not huge. So it's not just for huge data, but even for data that's a few thousand or tens of thousands. That's just nice. So anyway, okay. So this is what we want to do. We want to prove that even if we have some polynomial time algorithm, we want to see if it can be improved. And the goal of this complexity theory is to prove negative results, to show the limits. So to take a problem that, let's say, can be solved in n squared time and give formal evidence that it probably cannot. There's probably no n to the 2 minus epsilon time algorithm. For any epsilon, you cannot do it. Like you can do n to the 1.999 time.
According to deterministic error.
Yeah, so I'll talk about this, but yeah, you can think of it as any algorithm. Yeah, we will not really care about deterministic randomizing. And also in the model, like I'll mention this, but the model is just the model, the word round, like the standard model you think about when you do algorithms. Like in your algorithms course, like whatever operations you were allowed, this is what we want to allow. Okay, so how do we do this? How do we improve such negative results? Now let's look at a few things that you might think about. First of all, NP hardness is useless. I mean, it doesn't distinguish the different polynomial running time. Other thing is you probably remember this. For sorting, you've seen this comparison. If you in a model where you are only allowed compare numbers, you can prove this n log n lower bound for sorting. So one could do things like that. Say that if the algorithm is restricted in some way, then the number of operations is so and so. But these models you can usually break them. So for sorting, you can break the n log n with some more operations and so on. But these don't give us like a general complete answer. So we're not satisfied by those kinds of results. I mean, they are great when you can prove them, but we are looking for something that like any algorithm cannot do better. And the best thing would be to prove these things unconditionally with mathematical proofs that any algorithm, any circuit, any whatever Turing machine cannot do this in a certain amount of time. But the techniques that we have today, after many decades of work on this, they are very, very far from proving anything like that. So, for example, for SAT, the classical NP-hard problem, we cannot prove that you cannot solve it in better than like 3.1 times n. So we can't rule out n log n time for SAT. So we were talking about polynomial problems. So it's really kind of hopeless in the near future. Hopefully it will be done, but if you want to know the answers now, this is seems like we need to take a different. Now just say there's this time hierarchy theorem from complexity that tells us there are problems that require n squared time, but these are things you prove them with diagonalization typically. So the problems you get are some artificial. We want the results for natural problems that we actually want to solve. So okay, so how do we do this? The approach in this body of work is to kind of look at NP hardness and try to imitate it. So in NP hardness, what do? You start from some conjecture, a bit different from NP conjecture. It says that SAT cannot be solved in polynomial time. It's equivalent to the P different from NP conjecture. And then you show reductions. And these reductions, you take a problem, you show that it's NP hard, which means that if you could solve this problem in polynomial time, then the conjecture breaks. Then it would be equal to NP and would solve SAT faster and so on. This is what you would use as your evidence that it cannot be solved faster. And here we do the same, but somehow because the results we're looking for are more precise, more stronger, we need to make stronger assumptions. So the assumptions we make here, we make several, I'll get to them, but just one example is probably the most famous and popular in this field, is the strong exponential time hypothesis, which says that not only can you not solve that in polynomial time, you can solve it even a bit better than 2 to the n. So you cannot do 1.99 to the n for pizza. It's a stronger, it's like p different from NP, but stronger. And then we do reductions. So we take a problem, we want to show you cannot solve it fast. We show a reduction that says that if you could solve this problem fast, let's say in linear time, then you would somehow solve that faster and this conjecture works. So here's an example for this kind of result. So for the same local alignment problem we saw earlier, one could show that if you solve it in subquadratic time by an optimal exact algorithm, 1.99 times, then you can translate this into a 1.99 to the n algorithm for SAT, and this will break this this conjecture. So this is a kind of lower bound statements we have in this body of work. So let me be a bit more precise about this conjecture, the strong this will not matter for the talk, but if you want to see the definition, I'm going to show you. But you could just think of it as what I said. Cannot solve SAT in 1.99 to the n. So the conjecture specifically is about k-SAT, which is this problem where you get a CNF formula and you want to know if it's satisfiable. Meaning, so this formula has some variables, n variables, and you want to know if there's an assignment to the variables that makes the formula output true. And the formula is a CNF, so it's just an AND of ORs. And so it's an AND of clauses. Each clause has up to k literals, like variables order negation. This is just k-SAT. I mean, 3-SAT is the same with k equals 3. And yeah, so what's the complexity of this problem? So 2 to the n is the trivial thing. You could try all possible assignments. Then for small k, like for 3-SAT, you can actually do better. So there are these algorithms that do some kind of random walks, or it doesn't matter exactly how, but there's some clever things you can do and break the 2 to the n bound. But all of these algorithms, they have this kind of running time form. So there's some constant c that has been improving over the years, but the general form of the running time is like this. So if k goes to infinity, the improvement diminishes, and you get 2 to the n. The conjecture is that there is no epsilon such that in 2 minus epsilon to the n, you can solve k-SAT for all k. And so this conjecture actually was somehow suggested 2 decades ago by complexity theorists who were just studying SAT, because it's a very canonical problem there, and they were saying, okay, maybe it's, we don't know how to do anything about it. This is a reasonable conjecture. Let's look at it. It's interesting. And they had some, connections to other things in complexity for it. But it took like much longer until we started using it for reductions. So as I'm going to show you, I mean, by now we have a lot of results based on this conjecture for polynomial time problems. Yes, the way it's stated doesn't matter, but typically when you talk about 2 to the n, you suppress polynomial factors. Yeah. For example, these bounds are this times some poly n. Yeah. And in polynomial time, we will be suppressing polylog factors. So I want to mention a couple more problems. I mean, I've mentioned a lot of problems. You don't worry about remembering that. Just to give you a flavor. So okay, we saw this result for this bioinformatics problem. It's somehow a complicated problem. So let's look at like a much simpler problem that's similar. So this is probably like the simplest problem on sequences, on strings, that we don't know how to solve in near linear time. The longest common subsequence. You have 2 sequences, length n, and you just want to find the longest sequence that appears in both of them. So for example, this D, B, B, A, B, C. This is a subsequence that can be found in both of them. So you just want to find the longest one. And probably in some exercise in your algorithms class, you have solved this in n squared time with dynamic programming. You can shave the log squared factor by something called for Russian techniques. It's kind of simple. And it's been open, for many decades to improve this quadratic. And similar, again, is this edit distance problem. You have two strings and you want to transform one into the other with minimum number of operations. And again, you can do some dynamic program. So, following the result on local alignment was a breakthrough.
The n square by log square is also a dynamic program.
Dynamic programming, where you remember in dynamic programming, you have these entries. You fill each entry by looking at the previous ones, like next to it.
Right.
So you make this n squared steps. So in this for Russians technique, you make small blocks of log n by log or epsilon log n by epsilon log n, and you memorize kind of how to fill any small block. I mean, the total number of blocks is small, but it's just logged inside blocks. So you have this lookup table, a very big lookup table, and then you fill the dynamic programming block by block. So you shave a log squared factor. That's basically the trick.
In most finite complexity algorithms, you get dynamic programming based, or is that the main technique?
No, so the ones I mentioned so far is mostly dynamic programming, but I'll mention now a few other problems where it's usually exhaustive search or something. So you could also, like SAT, the algorithms for SAT are not dynamic programming. They're just, brute force, like 2 to the n.
No, I'm saying find it, like n square or algorithm.
Yeah.
For them, is it mainly dynamic programming or other techniques, or greedy or other techniques also?
Yeah, other techniques. Yeah. Actually, the most frequent is just brute force.
So, why 4 Russians?
Sorry? Oh, why is it called for Russians? It's this paper introducing it by 4 people. I'm not sure they're Russians, but maybe Bulgarian or some of them are Russians. But this is like a famous name for this technique. Yeah, for a lot of problems in polynomial time, you can shave some logs. So yeah, so by now we know that even these more simple problems like edit distance and log common subsequence, we have the same kinds of lower bounds. If you solve them in subquadratic time, you break this condition. And so here's a longer list of problems. So besides these, the ones I mentioned, there's a lot more problems. So we can draw this kind of subclass within the class P. So we have the class P of polynomial time problems. There's the subclass of set hard problems. So for each problem here, we have some polynomial running time. If you improve it by a little bit, by an n to the epsilon factor, you get a faster algorithm for k-set. You break this conjecture. And so the nice thing, or what I want to point out about this list, is that it's a very diverse list with a lot of very fundamental problems from a lot of topics. So we've already seen like these, problems on strings. There's this diameter problem. You have a graph with, let's say, n edges. You want to find the largest distance in the graph. You can do this in n squared time, and the conjecture. If you could do this in subquadratic time, you break the set. It's a very simple graph problem. Problems like on kind of strict geometry, where you have points in some dimension, and you want to find the closest pair. Doing that, so that you can solve by brute force. Just try all pairs and find the closest one. But solving it in subquadratic time, it's hard. So some variants of maximum flow, which I'll mention later. Subtree isomorphism is a nice one. You have 2 binary trees. You want to know if one is contained in the other. You can do n squared.
All these are the subquadratic we are saying, but there's few subcubic kind of problems as well, or mainly focusing on subquadratic, and they said it's mostly transferable to subquadratic.
Yeah, so actually, the ones on the list are subquadratic, but we have results that are also for cubic and so on.
K-set is the starting problem, and you can reduce to other problems to get cubic or.
Yes. So actually, there's like a problem in the middle here, which I haven't mentioned explicitly, but it's called the orthogonal vectors. You have a bunch of binary vectors, and you want to find if there is a pair that's orthogonal, or like this joint pair. And that problem is like the intermediate problem for most of these reductions. In that problem, you can also make it like you're looking for 3 vectors that are orthogonal, and then that's n cubed. You're looking for 4. So there's
Another question is for quantum problem, there is a speed up which happens from any such like from n to n to 10.
Yeah, great. Yeah, I have some slides about this stuff.
And so, as in the world of classic reductions, these are bespoke reductions. Like you have to, it's not a single. Like you have to design gadgets.
Yeah. So most of these, some of them are just gadgets, like many one reduction, and take an instance and create another instance. But most of them are not like that. They make multiple calls to the problem. It's like a Turing reduction. So that if you have a faster algorithm for one, then you might call it many times and many instances, and then you will get a faster algorithm for the other.
So showing the hardness for these problems doesn't imply short exponential answers.
Yeah, so that's a great question. The results here, they only go in one direction. So this is not like in NP completeness. There, right, all the NP complete problems, you just solve one of them, all of them we would solve them faster. This here is not true. You solve this one faster, this one, that one breaks, but the other problems here, nothing happens as far as we know. So this is not an equivalence class. This is just a hardness class. In other words, what you said, if you prove, if you prove that problem is actually hard, you get that these problems are actually hard. But if you prove that this problem has some quadratic lower bound, you don't show anything for that. No, so they're only based on SETH. So ETH is the weaker version. It's like between either from NP and strong ETH. It says that you cannot solve SAT in 2 to the little of n time. So that one is not enough for us. It's not fine-grained enough. So yeah, so that's this class. It's a very kind of big class, but so there's a lot of props in P, and and before these results, these reductions, this was a mess. You could, if you wanna, there's all these problems. Each one has a polynomial time algorithm. Like you wanna work on a problem, you don't know which one to work on, right? And you pick one of these, get stuck, go to the next one, and so on. Like you don't know what. Like a mess, and now with these reductions we can draw a nicer picture. So we have this subclass that's hard to understand, but there's actually two others that I want to talk about, two other big classes. So now it's like a more ordered picture, and so one nice way to think about it is you shouldn't work on any of these problems really at this point. You will not be able to solve them, not because of the conjecture. But first, you have to solve that problem on top. Solving any of these problems is at least as hard as solving the one on top. So, like, if you want to make progress, first solve that one, and then make progress on it.
Is there any overlap between this problem, like these classes?
Yes, I'll also get to that, but yeah. So before we talk about these, let me just introduce these two other conjectures. So there's one conjecture about SAT that we talked about, and this is the second conjecture about three-sum.
So just before so the reason for picking those three as my quintessential problems is more like collected historical wisdom.
Great. So let me say. So SAT, we said, there was this conjecture from complexity, and then some 10 years later, maybe people started using this and noticing that actually, if you take this conjecture, you can get a lot of interesting results in polynomial time problems, and that's what happened. Here, for three-sum, it was very different. It's like the other way. So actually, what the story is, this is from the computational geometry community in the early 90s. So there, I mean, geometry, you have like problems on points in the plane, you have a point, and you want to find a line that passes through 2 points or something. People could solve this in linear time, and then they look at a slightly harder problem. If you want to find a line that passes through 3 points, then they couldn't solve it. They had a lot of the problems like this, and then somehow the community noticed that there's this one bottleneck, this three-sum problem, that's really the reason for all of them. There's this paper written by 2 people, but in the acknowledgement you see like 20 or 30 people acknowledged, which is like all the famous names in the community. And this paper has like 10 reductions. It says it reduced a threesome to all of these problems where it was, the most fundamental ones that they still couldn't solve. So this is like a different thing. This is not a problem that, you look at and you say, this is a hard problem. It's just a problem that the community is telling you, we need to solve this problem first. The third one, I'll mention it, but it's like, it goes both ways. So what is this threesome problem? You get n numbers, and you want to find 3 that sum to 0. Numbers, you can think of them as integers. Originally, they thought about them as real numbers, but later, now we just look at the integer case. It's simpler, gives more results, and so on. Equally hard as far as we go. So how do you solve this problem? Naively, it's n cubed. You try all triples of numbers, check if they sum to 0. There's like a popular interview question. How to get this to n squared? Some simple algorithm. And the conjecture is that you cannot do better. So again, you can change some logs, but the conjecture is you can't do truly subquadratic.
N squared, are they hiding some log set?
No, so actually, the n squared log n is kind of makes simpler. You can also do it without the log, especially if you use randomness. It's easy. If you don't want to use randomness, I think it can also be done, but it's a bit more tricky. So. Yeah, so one thing you can do is for all pairs of numbers, you hash you take the sum and you hash it. And then for every number, you look at the minus and look for it in the hash table. So if you find a collision, that's a threesome. Yeah. But there are other things you can do.
Noticeably, matrix multiplication doesn't create an appear actually. Looks like a more like in terms of it's sort of a revered problem, at least historically, in terms of the exponent. But
Yeah. So this is a very interesting problem. I mentioned this in a few places in the talk actually, but it's a problem where for our theory, I mean, it's a problem where it was n cubed, and you could have thought that this is the less, and people have thought that, but then it was broken, and it has been improving. But many of the experts think it will be n squared. So somehow the feeling is that it will be n squared. So there's two ways to go about this. Like one way is to say we really want to prove that 2.3 something is a lower bound and try to base it on these conjectures. But actually, what we have been doing really is to say let's just assume it's 2. So I mean, we don't expect to show that if you break 2.3 something, you refute strong ETH. Or that would be like amazing, because getting all the way to 2 is something that the experts believe can be done. It's just a matter of finding the right idea, but like at the end of days, it should be 2. Whereas these conjectures, we don't have any statement like that. These are conjectures where we don't have any kind of approach towards breaking them that seems reasonable. So if you proved such a result, a reduction from SAT to matrix multiplication, in a sense, we would think of it as an algorithm. But I mentioned matrix multiplication a few places. So threesome has also its hardness class. In geometry in the 90s, there were a lot of problems, like geometric problems. But in the last decade, we started also seeing combinatorial problems that we can reduce from threesome. Some new techniques. So one nice problem is dynamic maximum matching. You have a graph, and edges are added and deleted. And you want to, whenever there's an update, you want to know the size of the maximum matching in the graph. And so can you do it while making the updates, polylog? So you can, of course, do this by every time you have an update, recompute the answer. This will give you, some n time or m time, or some polynomial time. And if you could break that polynomial, I don't remember what it was, you could actually break threesome. So there's a tight lower bound. We'll also see another result on the threesome later in the talk for a graph problem. So in the third class is about all picture fast. So this is a graph problem, and this is a conjecture that was became popular because of a paper that blamed the hardness of a lot of problems on it, like threesome. But actually, like that paper said, this is already a conjecture in the community because this is like the classical distance problem. Like if you have a graph and some distance problem, APSP is like the problem that you would like to solve. And so it's also, it goes both ways. It's a conjecture that's very well believed on its own, right? So what's the problem? You have a graph on n nodes and up to n squared edges, and it's weighted, not directed but weighted. And you want to know all the distances. For every pair of nodes, you want to know the shortest path. So you could just run Dijkstra from every node. You would get n cubed log n, n times squared log n. And you could do some shave a log or whatever. And actually, you could shave a lot more logs. So there's been a lot of work trying to shave, to prove this, and only shaving log factors. And about 10 years ago, there was this breakthrough of shaving 2 to the square root log n factor. This is more than a polylog, but still not polynomial factor. The conjecture is that you cannot do better. And notice that if the graph was unweighted, then you could use matrix multiplication to solve this problem. There's some classical algorithms. But if you have weights, it's like you need a matrix multiplication on a semi-ring, and just min plus semi-ring. So like that, on that kind of that matrix multiplication problem, these techniques that we have Strassen and all these things, they don't work. There's well-known barriers to them. And so this conjecture says that this just cannot be done. If you have weights, you cannot use matrix multiplication, you just cannot solve that problem.
For the unweighted case, 2.37 is the best.
Yes. Yeah, the best is the matrix multiplication running time, which can be achieved for undirected time. And so this problem also has its hardness class, a lot of graph problems. So for example, let me tell you this example. This is probably the nicest, most surprising problem in the class, negative triangle. So you have a graph, it has n nodes and it has some edge weights. You want to find 3 nodes, triangle, but the sum of edge weights is negative. Very simple problem. If you try all triples, you will get n cubed very easy. If you could, it's a decision problem. Just you have to say yes or no. If you do this in subcubic time, you solve APSP in subcubic. So this actually is the problem you reduce from to show kind of essentially all of these results. Reducing APSP to a problem is kind of complicated because there's a lot of answers you have to compute and so on. But first you go to this problem and then you look at this. And so one thing special about this class is that most of it is actually an equivalence class. But the problem, because kind of APSP is a kind of a hard problem, it has a lot of answers and so on. You can, if you solve it faster, you solve most of these problems faster. So for example, this negative triangle, for every pair, you knew the shortest path, like you knew the 2-hop, you could get the 2-hop distance, then you could just check, you could get this in subcubic time. And you could just compare the edge with this, you would know if there's a negative triangle in subcubic time.
For dynamic algorithm, there is reversing and update time. So here, how do you connect, like update time maybe is connection. Reversing, do you have some assumption here with APSP, or what is this dynamic mechanism?
Oh, so yeah, so the ones that are equivalent are only the blue ones, and that's a good observation there. So dynamic problems, we don't have equivalence typically. So we have a reduction one way. So if you could, so this is a dynamic problem, right? You pre-process the graph, you update, and you say. This statement here is that if you could support all these updates efficiently, then you would solve APSP faster. But this is like natural, right? You take a static problem, you create some graph, and you get the answer. But the other way is we don't know how to show. Like if I solve this static problem faster, I don't know how to get a dynamic result out of it.
What about foursome? I mean, this
Foursome.
Foursome doesn't lie somewhere here.
It will be in some later slide, but it's foursome. The complexity is still n squared.
Okay.
So the algorithm I said with the pairs and
Okay.
you can look for pairs and pairs. You get foursome in quadratic time. But if you go to 5-sum, it's n cubed.
Are these conjectures like independent or they
Yeah, great question. I think it is in one slide, so I'll get to it. Okay, so yeah, what I want to do now is now to discuss some of these questions. Most of them, many of them you have already asked about. So So one thing, I'm going to start with some preliminary remarks before we do that. So as I said, we ignore log factors and we will ignore any n to the lift of 1. And there's two reasons for this. I mean, one is the high order question is to figure out the polynomial, like the quadratic. We are less interested in the polylog. I mean, shaving log factors can be very interesting, but notice here, like if you have a quadratic result bound and going from n polylog n to n or to n log n, it's kind of the log factor is more substantial. But here, when you have n squared or n cubed, the log factor is less substantial. So this is somehow partly why we don't care that much. But we actually care. There's another reason, which is that we have a lot of reductions here, and we're very happy about it. I mean, that's kind of the nice thing about this works, that we capture a lot of problems. And for those, we really need these log factors. So if you restrict the statements to not somehow lose log factors, like you would be much more restricted in the reductions, and you will not get that much results. So this is two reasons. The model, as I said, is the word RAM. If you don't know what this is, it's even better. It's just like whatever you use without thinking about it. And so this talk is like focused on the polynomial time problems, but you can do these reductions also between exponential time problems. Like SAT, strong ETH is about 2 to the n being the barrier for SAT. You can think about set cover, subset sum, these kinds of problems that have some 2 to the n bound, and you could look for reductions there and show that this the 2 is tied for this if it's tied for that one. There has been quite a few results on there too, but we're focusing here on the polynomial time problem. So like these two things are somehow related. And so this is something important. So we ignore randomness also. So we ignore it in the following sense. So the reductions, we are allowing randomized reductions. So all of the statements I'm telling you here, somehow, if you solve a problem faster, you would solve the other one, but maybe with a randomized algorithm. So maybe if you solve the problem deterministically, you would still get a randomized algorithm for the other part. And this is fine because, so the conjectures I'm talking about, they're equally believable if you allow randomness or you don't. I mean, okay, they're strictly more stronger when you allow randomness, but it would be equally amazing to break them with randomness. If you solve SAT in 1.9 to the n with a randomized algorithm, that would already be amazing. So the conjectures somehow are equally believable, and then again, reductions become much easier when you allow randomness. So that's why somehow we allow it. Although many of the reductions can be made deterministic. So this is just preliminary remarks about it. Now, in terms of current and research on this topic, I want to classify it into two kind of directions. So there's of course the direction of proving more and more results. Still problems where you don't have tight bounds, and we try to classify them, prove better lower bounds or maybe upper bounds. And then there's this other direction which tries to understand the foundations of this, like the conjectures. How are they related? Are there problems that are in the intersection, and so on. I would say there's less work here. Most people are just trying to prove more and more results, but there are some works, and let me try to say a few things about this.
The broad scheme of things, like in its standard in complexity world, it does connect to other models, for example, communication complex. So one specific problem that I'm kind of curious, like stable matching, I know has these query bounds that you do need to solicit and almost n square. Or like in preference orders, you almost need to read the other connections of that sort of thing. So if translate.
I think so. I mean, the problems we are looking at have been looked at in various models. And then sometimes there's also commonalities in techniques and so on. I can't tell you like a general kind of statement about it, but there are connections to very complex things and so on.
And with PCB or UVCAMs, do you appear in any of this technique or?
So it depends on what you mean by that. So in terms of hardness of approximation, I mentioned this. Like this is something that's very interesting and mostly open. In terms of the problems themselves, like unique games and so on, It's not in the classes. I mean, that conjecture is not a fine-grained one, so it's a problem where the question is not whether, but it would be nice to put it here and show that you need n to the 100th time for a unique game, or something like that. We don't know. Yeah, so kind of one question is, right, like, why do we need three? Why the three conjecture? Why can't we have one or something like that? And for example, if you could reduce that to three-sum, we would unify these two classes. We would just, everything here would be one circle. Just have SAT on top. And all you have to do is show a reduction from SAT to three-sum or APSP. And this is, of course, has been, one of the biggest open questions for this topic. But there's a barrier for this. It seems impossible. So there's this paper by a group from UT San Diego. They show that if you assume NSET, which is a non-deterministic variant of strong ETH, then there's no reduction. And so let me explain why and what this means. So this barrier is based on a gap in the non-deterministic complexity of problems. So think about SAT and try to think of a non-deterministic algorithm. So imagine like a prover-verifier game. Let's say you're a verifier, you want to run in faster than 2 to the n time. There's a prover who wants to tell you, to convince you that the formula is satisfiable or not satisfiable. Convince you that it's satisfiable, he just gives you an assignment, and that's very easy, you just check. So then it's like solving it in the yes case is very easy. But what if it's not satisfiable? How can he prove that it's not satisfiable? We know of no algorithm where he can prove it to you and you run more efficiently. Like a prover is useless for convincing you that it's not satisfiable. And this has been an open question for many years, and the NSET says that it's impossible. So even if you had like this non-deterministic power, you cannot break strong ETH. And then think about three-sum. So at first look, it might seem like it's the same thing. The prover can convince me that there's a three-sum by giving me the three numbers, great. And how can he convince me that there's no three-sum? It seems very hard. But actually, in this paper, they show there is a fast algorithm for this verification. So there is a way for the prover to convince you that there's no three-sum in subquadratic time. The verifier runs in subquadratic time. So I will not go into that, but suppose you believe this, then you don't expect a reduction. Because then you could, if you had a reduction, you would just run it, and then use the non-deterministic algorithm for three-sum and break and solve SAT faster with non-determinism. This is the NSET barrier, and it rules out reductions from SAT to three-sum or APSP. So that's kind of unfortunate. But I mean, it's also somehow to be expected because the reductions we're working with here are very stringent. Like you cannot do a lot of things, and when you're that fine-grained, you'd expect different problems to have different reasons for being hard. I think maybe the more surprising thing is that these classes are so large. Like a lot of people have said this to me. Like what is surprising is that you can unify a lot of problems under such conjecture with these stringent reductions. So then, okay, we cannot have one conjecture. That's unfortunate, but we would like to have better conjecture or something like this. And we want this because I mean, if you prove P equals NP, the world breaks, right? But what happens here if you solve SAT faster? Not much. Or if you solve three-sum faster, what happens? Okay, you solve this problem faster. That is great, but there's no further consequences. As we observed, like it doesn't even imply faster algorithms for the other problem. So yeah, we've been looking for reasons like what would happen if you break them. Getting more results would be nice. For SAT, actually, if you do break it, you get some breakthroughs in complexity theory, some new circuit lower bounds that we don't know how to prove. But these are, not interesting results by themselves. They're only interesting because you can't prove them. It's difficult to break it, but it's not. And so because of that, there's been some interest in replacing the conjecture with better ones or proving results with more kind of confidence. And so, for example, you could try to prove lower bounds under multiple conjectures. So there are problems that are in the intersection. So if you solve them faster, you break two conjectures. For example, the problem we'll see later the whole edge triangle problem, where you have a graph and you want to know for each edge whether it's in a triangle. And then there are also problems also related to triangles and graphs that are hard under three conjectures. These are problems with simple and cubed algorithms, and if you break it, if you improve it, you break three conjectures. And these things can be reduced to other problems. So there are some results have more confidence, but most results don't. So we wrote this paper, some time ago. We were hoping to, base everything on this. A lot of time has passed. It's not happening. I mean, it's very hard to use this problem to reduce to other problems. It's like a trade-off between how much confidence you want to have and the quantity of results. Another direction that's also similar of getting better conjectures, we look at better or stronger versions of set. So set is about satisfiability of a CNF formula, which is like the most simple form of formulas. You can look at circuit set. And you could conjecture that you cannot beat 2 to the n for circuit set, where you get a complicated circuit in one chip. So that can be used to prove some results, but not for most. And I just want to say something nice about this. So we have a reduction from circuit set to longest common subsequence in these problems. And so if you shave some log factors, so let's say you want to improve the 4 Russians from log squared to log to the 100. Because we're starting from a very hard problem, this would let you shave some polynomial factors here on this problem, which would already be very surprising, because circuit is something we believe is very obfuscating, like you cannot do anything. You break some crypto and you get some circuit overlaps out of it. So even shaving log factors can be interesting. But again, most results are not based on such strong.
NSEDH, the area that you mentioned, that does not rule out like a single problem sitting on top of all three.
Okay, so maybe we'll see it, but there are problems. There are problems that sit higher up, so you can reduce them to. You could imagine even artificial ones, but then these problems are not like well studied. Not like you could make like a conjecture and get a lot of things, but this conjecture would be less believable. So it's again a trade-off like this. So now let's talk about this other direction. So here, right, you want to classify your problems. Okay, lower bounds and upper bounds. Let me give you an example of a recent lower bound that we proved that I'm very excited about. It's about approximate shortest paths. So and this is like a general direction here of proving hardness of approximation results. So we have these problems, very important. Okay, we showed that you cannot solve them exactly fast, great, but okay, what about some approximation, like maybe a 1.1 approximation maybe would be good enough? Can we rule that out? And typically we don't know. So this is a general area in which we have very little results. So one of the biggest open questions in this field is show that you cannot get a 1 plus epsilon approximation for this at the distance LCS, like a really, really good approximation, really, really fast. The best algorithms we have, if you want near linear time, they have some large constant approximation. So they're pretty far from it. Another example of this maximum matching problem in dynamic graphs is, again, one of the biggest open questions in the field. Computing the maximum matching exactly is hard to do in a dynamic way, where you spend very little time on the updates, polylog time. The best upper bound gives you like a bit better than 2 approximation. Can you get a 1.001 approximation? And so somehow we seem to be lacking kind of strong techniques for proving hardness of approximation results. So in the classical NP hardness, we have these PCP theorems and so on. And this is like early days for this field. So there's like 2 general techniques that exist. One of them is distributed PCP. It proves a lot of results, doesn't prove anything here. I'm not going to this much in the talk, but closest pair type of problems and so on, it can do some things. There's this new technique, from last year that I want to tell you about short cycle removal. You're right, that's a good question. We typically call n polylog n, that's near linear. Actually, in this, the title of that paper is actually, it's like, constant approximation near linear time, but actually they get what we call almost linear time, which is n to the 1 plus little of 1. So some people call near linear, but it's, almost linear time. So I'm going to tell you about this new technique, which will, say something about approximate shortest path. So the question is now, we want to solve APSP, all pair shortest path, and we want to do it, with a good approximation, very fast. So APSP, right? There's the weighted case and the unweighted case. They're a bit different. If you want exact, the conjecture is that you need n cubed for the weighted case. For the unweighted, you can do n to the omega. Omega is the matrix multiplication exponent, like 2 point something. If you want the 1 plus epsilon approximation, like the best possible approximation, you can actually get n to the omega for the weighted case. There is this work doing better for larger approximations. So, weighted, for example, with 3 approximations, you can get n squared. And so, as I said, we usually assume omega is 2 in this field. Like when you have a result like this, for us, okay, our job is done. Okay, and at the end of the day, it will be n squared. So this seems like, okay, we kind of understand. 1 plus epsilon, we're done. But n squared is still a lot of time. What if you have a sparse graph or something? You want bounds that depend on the number of edges. So linear time for APSP is really like m time, m to the 1 plus little. So what can you do in linear time in the number of edges? And but then APSP, the answer is the output size n squared, so you have to define it a bit carefully. And I think this is like the most natural definition of the problem. You get a graph, you have to pre-process it in linear time, and then you get a query that asks for the distance between a pair of nodes. You need to answer that fast, n to the little of 1 time, like polylog time. What can you do? How well can you do this? So of course, you would like to do this exactly, right? But this is hard. I mean, you can already see this by, if you could solve this problem exactly, take any graph, reprocess it in n squared time, then for every pair, get the answer in polylog time, so that's n squared polylog in total, you would solve the exact APSP problem. So exact is hard, I mean, but what can you do approximately? So this kind of thing is usually called distance oracle. Heard of that? And so here we're asking about the pre-processing time distance oracle. So there's a classical distance oracle by Thorup and Zwick, which gives you this kind of bound. So you can solve this problem with pre-processing, that's m times some n to the something small, n to the 1 over k, and k is controlling the error. So with this time, you get 2k minus 1 error. So if you want to get closer and closer to linear time, you get worse and worse error. This is a classical expression. What do we know in terms of lower bounds? So I'll show you, it's kind of easy to show that breaking better than 2 approximation is going to be hard. So let me show you this reduction. This will be like the most technical part of the talk. So this lower bound will be based on either threesome or APSP, because we see a reduction from the all edge triangle problem, which is hard under both of these problems. So here's the reduction. So you have this graph. The problem is all edge triangle, which you can assume that the graph is tripartite for reasons. Then for every edge between B and C in that top part, you want to know if it's in a triangle. Which just means, you look at an edge, you want to know if there's a 2-path. That's the problem. The parameters will not matter that much, but the problem is hard when the degree is root n for every node, so you have n to the 1.5 edges, and the conjecture is you cannot break quadratic time. If you break quadratic time, you solve threesome and APSP fast. But the point is it's a super linear hard problem. You can't solve this in linear time, in the number of edges. So don't worry about the exact parameter. But it's not a problem you can solve in linear time. So how do you reduce from this problem to the distance oracle problem? You have this graph. You want to use a distance oracle to figure out if there's a triangle for every edge. So you take a graph and you create a new graph by just deleting the edges in this top part of the graph. You get this graph G point. And now you look at any pair BC that used to be an edge. And you ask what is the distance between this pair. So and then you get that distance is exactly 2 if the edge was in a triangle, right? Because if you have a 2 path, then when you add back the edge, you get a triangle. So if you go over all edges for that pair, the edge, you check if the distance is 2 or larger, then you know if that edge is on the If the edge is not in a triangle, then the distance between these 2 points, like the endpoint of the edge, is not 2, it's larger. This shows you that at least if you had an exact distance oracle, you would solve this problem in linear time. Why? Because suppose the pre-processing here is linear. The number of queries here is just the number of edges there. If you have constant time per query, then this is linear time. Okay. And now because you're checking here for distance 2 or 3 or above, this means that if you had a 3/2 minus epsilon approximation, you would distinguish the 2 cases. So you get a 1.5 lower for the factor. And I actually said that 2 is easy. And the reason 2 is easy is that, well, it's a bipartite graph. So if there's no 2 path, then you have to zigzag, like 1, 2, 3, 4. It would be 4. So it's actually a hardness for 2 minus epsilon. Now, okay, so can we prove a higher lower bound? So to prove a higher lower bound, you want to say, okay, if there's a triangle, it's 2. If there's no triangle, there's no path of length 100. If you could show that, then you would get that not just 2 approximations are, but 100 over 2 approximations. So you would hope that there's this gap here between either distance 2 or 100. Unfortunately, this will not happen because of this short cycle barrier. If you look at this pair that used to be an edge, suppose there was a short cycle for that pair, like a cycle length 5, right? 1, 2, 3, 4, 5. Then if you look here, you will have a distance 4. So if the pair was in a short cycle, you will not get a large gap. This is the barrier. This is why we cannot prove hardness above 2 in this technique. There was a paper by Tatrashko, Ziti, and Torov using different conjectures with some clever ideas. They got from 2 to 3. I'm not going to how they did it, but somehow they pushed this technique to the limit, make distances longer, like the 2 becomes smaller and so on. And they got all the way to 3, and even their technique gets stuck there because of essentially the same reason. And so this, is this 3 the best possible, right? This says that you cannot beat 3 if you want near linear running time, but the upper bound is super constant. So what we do is we look at actually this gap triangle problem. Right? You would like to have this gap between 2 and 100. So let's look at this problem. You have a graph. You want to know for every edge. In the S case, the edge is in a triangle. In the no case, the edge is not in a short cycle. There's no short cycle using that edge. And what we show is that this problem is hard. So we have a reduction from triangle from that problem without this restriction to the problem with the restriction. So finding a triangle in a graph that doesn't have short cycles or has very few of them, it's hard. And then we show that under these conjectures, 3-sum IISc, this trade-off is the best possible, up to the constants. So if you want to get this kind of running time, the error needs to grow. In particular, there is no constant approximation in almost linear time. Very recently, like a few months ago, there's 2 papers independently improving this to improve the constant. So in the previous paper, we had the constant was terrible. Now it's like super close to the classical upper bound. So towards this 2k minus 1, and we show that this k, 1 times k is a lower bound. Still a gap, but okay. So that was this result. So now back to like the high-level discussion of the topic. So of course, there's a lot of work proving more and more lower bounds, but somehow, maybe unfortunately, a lot of time these results introduce new conjectures. Actually, this is like the more accurate picture of the class P. Like not just this nice 3 class picture, but there's been about 10 or more other conjectures that are being introduced. So we have the 3 primary conjectures that I said, and then we have these secondary conjectures that are, using them we can prove more results. So these are very interesting problems, fundamental problems, that we could not put in any of these classes. But when we had a new conjecture, we could put them. And these are stronger conjectures in the sense that usually what they do is they take a hard problem and they say that it's still hard if you introduce some structure. In this particular example, it's not so clear, but this is the minimum weight K-clique problem. So you want to find a K-clique with minimum weight. You can reduce this to the 3-clique case, which is equivalent to IISc. So it is a stronger version. These secondary conjectures, I mean, they are usually, more recent ones, introduced more recently. They're about less extensively studied problems, and usually they are strictly stronger. So they are kind of less believable, less safe of conjectures, but they let us prove more results. And actually, this conjecture, the minimum weight K-clique, it unifies 2 conjectures. So if you assume it, you get all the lower bounds of IISp and all the lower bounds of Seth. It's a pretty interesting conjecture.
So what did it say exactly? That you need n power p times?
Exactly, that you need n to the k time. And yeah, I mean, there's other things like this strong threesome. Says that threesome you need n squared time even when the numbers are in small range. That's 1 to n squared. You can solve threesome in max number is u. You can solve it in u log n time. So things like that, and then you can prove more results. So this is like this is what's happening. But now I want to tell you that this is not that bad. I mean, I actually think this is not. I mean, some people look at this and say it's a terrible picture. Right? It's a mess. But I actually think of it as being very nice because what it tells you is that if you want to solve problems, these are the problems you should solve. You will not be able to solve these problems until you break the conjectures. And these, even weaker conjectures are really like the most attackable problems. You will not solve these faster until you solve the minimum weight K-clique problems. And usually, like the new conjectures are actually very basic problems, very nice. I mean, they're not somehow crazy, right? Like strong threesome. It's just threesome with small numbers. Like they're natural. They're really pinpointing where you should attack, and they're like the easiest hard problems.
So I tell you that IISc is more like n-cube kind of problems. threesome is more like n-squared type of problem. But C2 may not be the only exponent. The 1.5 or some other exponents are also important. So do you think for each of these exponents there is some canonical problem, or like there are multiple problems to consider for that, or
no, I don't think of it that way. I actually think of it. So think about like IISc is 3-clique, and K-clique is larger K. So if you have an n cube problem, maybe you start from IISc. If you have n to the 6th problem or so, you start from the 6th clique. So the conjectures are not about the running time; they're more about the structure, I would say. Then for each conjecture, there's this like layers, like the K-clique is the layer. Here also we have this orthogonal vectors problem. There's let's say 3 orthogonal or K orthogonal vectors. This gives you the control. So if you have an n to the 4 problem and it has the structure of this class, you would start with the orthogonal vector. So I would say each class is kind of parameterized with a.
But even your K is integer, so 2, 3, 4, 5. But do you think there are problems in 2.5 or some other fractional number?
Yeah, there are. So actually, IISc is not really 3, it's actually 1.5 because the number of edges is n squared.
Okay.
So the exponent is actually 1.5, and you can use this to prove 1.5 lower bounds. Yeah, but also like in reduction, sometimes this like 1.5 occurs, so it's not really.
Any secondary conjectures that were present earlier, but this too.
Oh, it's a great question. So there's 2. One not really related because it was about space-time trade-off. So for threesome, someone's conjectured that if you pre-process the numbers in a certain space, then you would need that much time afterwards. So you get like maybe a new set or something you want to solve free sum. So there was a conjecture that was disproved, but not like here. I'm really just talking about time complexity. For time complexity, there was a conjecture similar to strong ETH, but about some quadratic equations, solving them. That was disproved, but that one, I mean, it wasn't that popular. Like it was used in one paper or something. Also, yeah. Now I'll mention a result that also disproves one conjecture, but again, used only in one paper. But the one wasn't really something big yet.
Yeah, hardness results based on average case assumptions.
I'll also get to that, but yeah. You can make average case versions of this. We don't know yet worst case to average case very much, but yeah. Maybe I'll mention this later. So yeah, so now I want to somehow motivate this point that, you know, like one of the things I like the most about this theory, maybe not necessarily that it's telling us the truth about the problems, like which ones are hard, and like that's great. But the one thing which is sort of what like we're looking at really, is to really help algorithm design. Like really tell you like which problems, or tell researchers what problems to attack. I think this is very productive. And now I just want to give you one example that somehow to prove this to you, which is a problem you have heard about earlier today. I'll just talk about this for a few minutes. Just give you this other angle on fine-grained complexity. So all pairs max flow, right? I mean, those of you who are here, you heard about this new result that we have for this problem. So you can think, okay, how does this relate to APSP and so on? Because, right, I mean, we solve so the intuition a lot of people have is that actually max flow should be harder than shortest path. And so we are saying that all pair shortest path is a hard problem. Then Debmalia showed you that all pair max flow can be solved very easily. So what's going on? So let me somehow. Let's compare these two problems, right? Shortest path and max flow. These very basic classical problems. Right, in max flow, you have S and T. You want to find to push the maximum amount of flow, respecting the edge capacities, which you can think of as just finding the minimum cut that separates S and T, the cheapest amount of edges to delete. And shortest path is just the cheapest way to go from S to T. So, like, which of these two problems is easier? Which is harder? Right, and shortest path, like in this ST version where we have the pair, it's a very easy problem. You just run the extra, and you get the answer. Right? And it's classical times we have this. For max flow, right? It wasn't that easy. There was these polynomial time algorithms in the 70s, and then in the last decade or so, there's these methods using continuous optimization that improved the polynomials, and since then, like the experts have been telling us, okay, these techniques are very powerful. It will get to linear time, just a matter of a few years, and so on. And last year it was actually accomplished. So this paper at Fox actually solved the problem in linear time, almost linear time. So what this means is, okay, this is like very, very simple. Half a page thing, algorithm paper. This is a 100-page paper, and so on. So like max flow is more complicated, but it's not harder. There's no separation here. You ignore the subpolynomial factor. Okay. But actually, right, this problem solves a more general problem. This Dijkstra's algorithm, when you run it, you don't just get the ST distance, you get the single source distance at the same cost, so from S to all the targets. And here it's not so clear, right? You run this algorithm, you just get one pair. You want to know for another pair, you have to run it again and again. So if you look at the more general all pairs problem, maybe you would hope to get some separation, right? So now you have a graph and you want to know for every pair what is the distance, or for every pair what is the flow. So these are APSP and APMF. So which one is easier? The trivial algorithm for both is just for every pair run the linear time algorithm that we saw, the quadratic algorithm. And when m is up to n squared. So this would be n to the 4. But here, because we also at the same cost of running it once, we get the single source, this will just be n. And then here there was this Gomori-Hu result. Very, very nice breakthrough where they show that you can actually get the same kind of bound for APMF. Just n times max flow. So you get n cubed here. And since that result, right, it was open how to break this n bound. Can you get little of n times max flow, which has remained open for many years, and then for APSP there were these small improvements. So maybe it felt like if one of them will be broken, maybe it would. And in any case, like the feeling we had, right, was that this problem should be at least as hard as that problem. I mean, max flow is at least as hard as shortest pass. There should be a reduction in shortness. And this was kind of our feeling going in, right? That we should. I mean, this from the beginning of my PhD. This was something I was working on. Just take this problem, put it in this class, and be done. And we did have some results along these lines. So in directed graphs, not in. If you add the power of directed graphs, we could show hardness results that show that max flow is harder than shortest path. Or for sparse graph single source, we could show quadratic, which depends on linear time. For all pairs max flow, we've got a cubic bound. These are all understood. And under some other conjectures like Fourier, we can even show that you cannot get cubic time. So the Gomori result that gets cubic time is only for undirected graphs. For directed graphs, we could show a super cubic lower bound for APSP. So what this says is that, yes, like our intuition is confirmed, max flow is harder than shortest path, but only in directed graphs. And this is not really the most interesting setting because directed graphs, the Gomori result, this super fundamental result doesn't apply. So the main question right on our mind was non-directed graphs, what is going on, and we didn't have any hardness results. Here's where I want to give like conceptual credit to the fine-grained complexity because this is just some of the nicest problems in my opinion to attack, right? Like very nice problems. All of them, there was no improvement in many decades for each of them. So if I wanted to work on any of them, like why would I pick all pairs max flow out of them? Like why that one, right? We'd just be too distracted by all the other problems and so on. But then after we had these reductions, hardness results. We could say, okay, we could either attack the red ones, these conjectures that, like we have isolated as very hard and so on. Maybe I don't feel that ambitious today, like to attack a conjecture. But then all these other problems, like I shouldn't really work on them anymore because I will not be able to solve them until I solve the red ones. Then all pairs max flow was left as a very interesting special problem where I don't know that it's as hard as breaking a conjecture. So this is like, so we worked on this for many years, and this is what, just a one slide summary of what we found. And so we had this hardness for directed graphs, then we were looking at undirected graphs. We couldn't show any hardness, so we started looking for an explanation. So we looked at this barrier with NSET, and so we actually showed the non-deterministic algorithm for the problem, which was an excuse for why we can't prove hardness. And then we looked at this non-deterministic algorithm, and we somehow extracted interesting results out of it, which said that you can reduce the all pairs max flow or the Gomori problem to the single source problem, which that Maya probably mentioned. And then we continued working on it, and we had for unweighted graph we broke the Gomori bound cubic time. We were very happy. Then we continued working on it. There was this 3 papers independently getting this squared, and this was like the first point in history where all pairs max flow suddenly became easier than shortest path in terms of running time. Like up to that point, of course, it was always larger complexity, but here we had this separation, the opposite of what we expected. But again, at the end of days, right, omega is 2, so this wasn't really a separation. So this was not a true separation, but somehow. Okay. Then with these guys, we got the result that Dimani mentioned. So this with Robbie Kurgamer, Mahat Fadalsi, Jason Lee, Dimani, Satya Sarno. So this is the updated picture, right? So very strong separation. If you believe the APSP conjecture. So the APSP conjecture says that okay, even if omega is 2, even if if we're very, very optimistic, we will still not know how to break the cubic bound. And for APMF, it's already done. So one thing to me and a lot of people, this intuitively, this makes us maybe suspicious of the APSP conjecture. And just like, when people were introducing the APSP, like they were saying, we have these n squared things you have to compute. For each one, you have to spend n time. Like, how can you do better than that? Okay, now just to further like drive this point of how focusing on how these lower bounds really direct us to the solvable problems, I want to give just a few more examples of recent results. So there was this. So I mentioned like the biggest open question in the field has been for many years in terms of hardness approximation to prove that you cannot get a very good approximation for edit distance near linear time. And then there's this group which got the best paper at Fox where they got an algorithm. They didn't solve that. I mean, before their work, the best approximation was a polylog n factor. And they got a constant factor approximation. And they say it explicitly that they are motivated by the lack of lower bounds for the problem. Since then, this technique that they introduced has led to a lot of exciting breakthroughs for other problems. Another paper where the author explicitly mentions that he was looking at trying to prove lower bounds for a problem and then got an upper bound is the diameter problem in planar graphs. So diameter is computing the largest distance in a graph. We have an n squared lower bound in sparse graphs, but if the graph is planar now, can you do better than quadratic? This is in planar graphs. A lot of things become linear time. It become very easy, and this is an annoying problem where it wasn't. It's just quadratic. And so Sergio Cabello got the best paper at Soda where he got some into the 1.8 algorithm for the problem. Just like that one, I mean, here it's still open to prove a super linear lower bound. We still have no lower bound. The upper bound is like into the 1.66. And in a few weeks, right, the best paper at Soda, there's two papers, both with the same result. This award, they got better than 2 approximation for matching in dynamic graphs with polylog n uplift.
Actually, it's got 23.
Thanks. I don't know why I thought 22. Okay, so that's it in terms of these two kind of main directions. Now let's quickly talk about the third direction that's somehow kind of orthogonal to all of this. It's kind of everything we're looking at is like time complexity and worst case and so on. We could look at other things. For example, the average case complexity. So what's happening there? So we assume that the problems are hard against randomized algorithms, but we don't necessarily assume that they are hard on a random input. So think of a uniformly random graph or 3-sum with uniform number drawn from some natural distribution. Maybe it's hard, maybe we don't really know. Sometimes we know, but a lot of distributions we don't know that it's easy. But we would like to prove this. So show a reduction from the worst case to the average case that would prove this. So the other way would just be to make a conjecture that this problem is hard in the average case, and then try to classify problems that way. These things is what kind of people have been working on. And there's been a lot of progress on this, but we still don't have like what we would like to have these strong worst case to average case reductions. I'm just giving you some pointers to some recent papers. I will not go into the details. And I'll just say like this is highly motivated by cryptography. So in cryptography, you usually start from hard problems and you create some crypto out of them, some encryption schemes that whose security is based on these hard problems. And people are interested in doing like fine-grained crypto for various reasons. Like, for example, here we make more precise assumptions on the complexity. So you would like to know more precisely how hard are problems so that you know how to set your parameters and practice more precisely. Or because even if P equals NP, you would still like to have some hardness like n squared and so on. So there's some motivations for this. And for that, you would really need average case. Like you cannot build crypto without the ability to sample a hard instance and so on. And so there is an interesting paper showing some public key encryption, some crypto. If you may assume that these triangle problems are hard under some uniform distribution. This is just like one slide about this, and now about quantum. So someone asked earlier about what happens with quantum computers. So there is recent works on this. Kind of one sentence summary is that yes, you can apply Grover search. So Grover search is this very powerful hammer that lets you shave a square root factor. And then there's a lot of interesting work trying to understand, does it always work or not always work? So for the conjectures, it does work very well. So for that, you can just apply Grover search, and you would get a square root improvement. So from 2 to the n, you go to the 2 to the n over 2. And then you could make this quantum Seth conjecture that people have made, which says that this is the best possible quantum. So like, which can make sense. I mean, you can apply Grover, but somehow breaking it further, you will need new ideas that will somehow really also break it in the classical world. But this is not the formal proof or anything. And then when you make that conjecture, you can look at the reductions. You can try to make them work in a quantum way, and then prove that, okay, this problem you can solve in linear time, but you cannot solve in sublinear time in quantum. The same happens there. One thing that I want to mention, and the most interesting things for me, that these like dynamic programming problems, Grover search doesn't help there. They're like too sequential. It's a big open question to get sub-quadratic quantum algorithms. Okay, finally, I'll just mention there's a lot more work that I will not cover here. So approximations, we already said, it's like not exact algorithm, but approximations. There are results looking at restricted inputs, like proving hardness for planar graphs, things like that. Linear algebra problems. So everything I'm talking about is really like combinatorial, but there's interesting problems in algebra where people have been trying to get reductions, space-time trade-offs. Yeah, I'll stop here. Happy to take questions. No, so that's so K-sum is there. You could make a K-sum conjecture, and I've made it, which would be that you need n to the ceiling of K over 2. Like for 5 sum, you need n cube. This does not reduce to 3 sum. There's no connection between them. If you break 3 sum, you don't break 5 sum. But 5 sum lets you prove sometimes more results. For the even ones, there is a reduction. So if you break 4 sum, you will break 8 sum.
Is there a fine-grained version for space, like where you cannot solve it in sublinear space or subquadratic space, something else? Is the space?
There's a few results like this, but not like a large amount. Yeah. And most of the problems here are actually easy for like classically for space or this. Like 3 sum. For set, you need just actually 3 sum is not so easy for space. You have polylog space or log space. I don't think it's know how to get quadratic time for 3 sum.
For some API problem, knapsack, etc. If you want to get exact algorithm, you need some space, like 2 or n by 4 or something.
Exactly. Yeah. So 3 sum is kind of like that. If you want to get the quadratic time, you need Newton space. To restrict your stress further to polylog space, then you need cubic time. Other problems, negative triangle problems are usually easy on space. You get cubic time, which is the best we know. You don't need much space.
If the length is looked at like has completely applied to like higher levels, for example, like problems in vehicle intersections or complicated problems where there are polynomials and but it's genuinely like into the 20.
I see.
Cunningham style results, more complicated. It may try Boolean, for example. There are persons with it, really, even submodular minimization, for example. It's about polynomial time, but yeah, not much beyond into the Q.
Yeah, we don't know. I mean, I think people have looked at this to some extent. For example, for linear programming, we've looked at this a lot. And we don't know how to prove anything for linear. Problems you're mentioning are even harder.
Yeah, kind of.
So maybe there's hope, but not familiar with any actual results.
So these space lower bounds in data streaming, which are mostly based on computation complexity, is there some connection between that and UGC words?
So there are some reductions here that were used to prove streaming results. Partly because this problem here is like this orthogonal vectors. It's like disjoint pair, which has disjointness in it. So some of the gadgets have been used, but I would say like anecdotal things like that. There is this quantum Seth paper making some interesting conjectures relating query complexity to time complexity, saying that if you have some function that's hard for queries, then it's also hard for time in a certain way. So there's some examples like this, but not a general.
General question. To learn about this, what are the best resources? So there's a standard textbook or something. So
No textbook, but there's a few courses with some lecture notes.
I think you also taught a code, but the videos are not publicly available like this.
I see. Yeah, I should make them. I don't know how, but right. Yeah, I don't know of a course with a publicly available videos. Sorry? Yeah, you can ask for a Weizmann login. You would get. But I can probably make them public.
Hardness has improved. Like, for example, sorting can be do using things that can be done better than in loving. Any like more difficult problems which have hardness has improved.
No, I mean, this depends on, so you can restrict the model and then you can prove something. For example, so there's this like comparison base for all pair shortest paths. There's some paper saying you can only compare paths. You can look at paths and compare their length. There they proved an n cubed lower bound. But then that was actually broken, like this n squared shaving log factors, they go beyond that. So, and also for edit distance, there was something like that with like restricting to dynamic programming kind of approaches. And then, so yeah, when you make enough restrictions, you can prove something. But like a general lower bound that holds for any algorithm, we haven't for no problem, like not even for SAT. Even for sorting, I mean, the lower bound is not for general algorithm. Strong APSP, it's APSP where the weights are from 1 to n. So integers from 1 to n. The conjecture is you still need cubic time. If you restrict them further, it can be done. So there's maximum weight times n to the omega algorithm. So if omega is 2 and the maximum weight is a bit smaller. You could call them that. I mean, if you call the comparison-based sorting information theoretic, then yeah, they are information theoretic. And they're, But I mean, these hardness results, I would say they are the ones I'm thinking about. They're from the 70s and 80s. Like it's not really something that's very active these days. There are results looking at circuit lower bounds for these things and restricting the circuit model, like constant depth circuits and so on. That is more active. But it's different, right? Because I mean, the classical results, they look at operations that you expect to do in an algorithm and say, okay, with these operations you will not do it. Circuit is more like a general model of computation, with some restrictions, but they don't necessarily come because of what you expect to do in the algorithm.
There are no questions at this time.
Thank you.
Thanks so much.
We have coffee snack and being ready, right? 4:30.
What